morning, students. This is Dr.GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today, in this session, I would like to explain about shaft design. So generally, the shafts are classified into two types. One is transmission shaft, another one is mission shafts. The shafts are used for power transmission for one place to another place. So always it is a circular cross section. Transmission shafts, example is line shafts. It carry power transmission from one place to another place with the help of other machine elements like gears and the belt pulleys. In case of machine shaft, the shaft integrated itself with the machine. Example, lathe spindle and our vehicle axle and spline shaft. These all are the machine shaft. While carrying power transmission, the shafts are undergone some stresses due to various loads. While designing a shaft, you should know the forces acting on the shaft. What are the vertical forces acting and what are the horizontal forces acting on that shaft? And any other machine elements are mounted on shaft or not, you should check. If mounted any machine elements, gears or the belt pulleys, you should consider their transmission force also. So all these things we will discuss in this session. The shaft design is based on two criteria. One is strength basis, another one is torsional rigidity. Now we will see, so what is the strength basis design and what is the torsional rigidity design. In designing of shafts on the basis of strength, the following cases may be considered. What are they? One is the shaft subjected to twisting movement or torque only. Second one, when the shaft subjected to bending movement, there is no twisting movement. It only subjected to bending movement. Third one is shaft subjected to combined twisting and bending movements. And the fourth one, shafts are subjected to axial loads in addition to combined torsional and bending loads. So that's why first you select the criteria, say at what basis how to design the shaft, what are the given loads. So when it is subjected to torsional loads, you should take first criteria. It is subjected to bending moment, the second criteria. Sometimes the combination of these two, the torque and bending moment also will act on the shaft due to the combined loads. So how to design of a shaft while it is subjected to bending and torsion. Similarly, the fourth one, in addition to the torsion and bending moment, another axial load also sometimes will act on shaft. Okay? So all these things one by one we will discuss. First we will take shaft subjected to twisting moment or torque. When the shaft is subjected to a twisting moment, or we can say torque, then the diameter of the shaft may be obtained by using the torsion equation. So in this case, first case, you should use torsion equation. So what is the torsion equation? T by J is equal to tau by R. Here given, the T by J is equal to tau by R. So what is T? T is here twisting moment acting upon the shaft. First you should calculate torsion, torque, how much torque transmitted the shaft. Second one, polar moment of inertia of the shaft about the axis of the rotation. And tau is torsional shear stress. The torsional shear stress will induce due to the twisting moment, torsion loads. The normal shear stress will be induced due to the direct loads, direct shear loads. Clear? So next R is the distance from neutral axis to the outermost fiber. So that is, you can take a radius, so half of the diameter. So where D is the diameter of the shaft. So already we know that for round solid shaft, the polar moment of inertia J is equal to pi by 32 into d to the power of 4, where D is here diameter of the shaft. This is for solid shaft. So for hollow shaft, I will tell you next slide. So in this above equation, you can write the T by J is equal to tau by R equation. You can write like this. So substitute J value in this. So pi by 32 into d to the power of 4. This is polar moment of inertia for solid circular shaft. And d by 2. So we will get the final equation. T is equal to pi by 16 into tau into d cube. Clear? So here the shear stress, torsional shear stress, and d is the diameter. T is the torsion. So by using this equation, you may calculate d value, the diameter of the shaft. See, next, in the case of a hollow shaft, the J is equal to pi by 32 into d naught to the power of 4 minus di to the power of 4. So what is d naught and di? D naught is outer diameter of the shaft. So this is for hollow shaft. So hollow shaft having two dias, inner and outer diameter. The inner diameter di and outer diameter d naught. So substitute this J value in the previous equation. T by J is equal to tau by R. So substitute this J value in this equation. You will get the T is equal to pi by 16 into tau into d naught to the power of 4 minus di to the power of 4 divided by d. For simplicity, let take A and K ratio of inside diameter and outside diameter of the shaft. K is equal to di to the power of di divided by d naught. So substitute this value in this equation. So we will get another equation, that is T is equal to pi by 16 into tau into d naught to the power of 4 divided by d naught, and multiply with 1 minus di by d naught to the power of 4. So finally, we will get pi by 16 into tau into d naught cube into 1 minus k to the power of 4. So from the above the equations, two equation, third and fourth, the outside and inside diameter of a hollow shaft may be determined. So in this, you should calculate diameter of the outer diameter of the shaft and di, inside diameter of the shaft. In previous case, in solid shaft, so there is one diameter. So the why? Because the solid shaft having only one diameter, the outside diameter, that is d. So you may determine by using previous equation. T is equal to pi by 16 into tau into d cube. But in this case, instead of this d, he will get d naught to the power of 3 into 1 minus k to the power of 4. What is k? K is di by d naught. It is ratio of inner diameter to the outer diameter of the shaft. Clear? So the twisting moment may be obtained by using the following relation. So how do we calculate that torsion? So by using P is equal to 2 pi nt by 60. Power is equal to 2 pi nt by 60. N is the number of revolutions of the shaft, that is speed of the shaft, and T is twisting moment in Newton meter. If you know the power value, you can calculate twisting moment. T is equal to 60p by 2 pi n. Use this equation for calculation of twisting moment. In case of belt drives, the twisting moment T is equal to T1 minus T2 multiplied with R. What is T1 and T2? T1 and T2 tensions of belts. One is slack side tension, another one is tight side tension. Next, second case. When the shaft is subjected to bending moment, there is no twisting moment. The shaft is subject to only bending moment. So while designing of shaft, you should consider only bending moment equation. Why? Because the shaft is subjected to bending loads. Then the maximum stress, it may be tensile or compressive, is given by the bending equation. So bending equation apply. So the bending equation is equal to M by I is equal to sigma by Y. So what is the bending equation? M by I is equal to sigma by Y is equal to E by R. So the actual bending equation, this one. But we will take up to here only. M by I is equal to sigma by Y. We don't need this E by R. Where M is the bending moment, I is moment of inertia of cross-sectional area of the shaft, sigma B is the bending stress, and Y is the distance from neutral axis to the outermost fiber. And already we know the round solid shaft moment of inertia I is equal to pi by 64 into d to the power of 4. The Y is equal to d by 2. So I value and Y value substitute in this equation, the bending moment equation, M by I is equal to sigma by Y. You will get another equation. So that is M is equal to pi by 32 into sigma B into dq. So calculate the bending moment and sigma B. So sometimes they may give the bending moment value and the sigma B in a problem. Then you may calculate the diameter of the shaft when it is subjected to bending moment. See the difference between this twisting moment and bending moment. The previous case, the shaft is subjected to twisting moment. In that case, only torque you need to calculate. T is equal to pi by 16 tau into dq. But in this case, the bending moment, in place of T, the bending moment will come. And in place of this pi by 16, pi by 32 into d to the power of pi by 32 into d cube. In case of in place of shear stress, sigma B, the bending stress will come. Clear? So from this equation, the diameter of the solid shaft you may be obtained, you may be calculated. So also know that for a hollow shaft, the moment of inertia. So up to now, we have written equation for solid shaft. For a hollow shaft case, again write down the I moment of inertia. So that is I is equal to pi by 64 into d naught to the power of 4 into 1 minus k to the power of 4. Y is d naught by 2. Again substituting these values in equation 1. So you will get finally pi by 32 into sigma B into d naught cube into 1 minus k to the power of 4. By using this equation, you may calculate outer diameter of the shaft, d naught. If you know the d naught, you can calculate di. Why? Because k is equal to di by d naught. And next case, third case, shaft subjected to combined twisting and bending moment. In this case, see, the combination of torsion loads and bending loads will act on the shaft. In this case, the shaft must be designed on the basis of two moments. And you should take two theories. So already you know theories of failures or 5 theories are there for safe design. Yet the following two theories are important from the subject point of view. So what are they? One is the maximum shear stress theory. So also you can say guest theory. Always it is used for ductile materials. So what are the ductile materials? Like steel and mild steel. And second one is maximum principal stress theory or normal stress theory, or you can say Rankine's theory. Another name is Rankine's theory. Always this theory is used for brittle materials. Example, cast iron. When the shaft is subjected to twisting movement and bending movement, you should consider these two theories. First, you design of shaft on the basis of maximum shear stress theory. So according to this maximum shear stress theory, what is the value of diameter? Find out. Similarly, second case, apply maximum normal stress theory, Rankine's theory. Calculate diameter of the shaft. Clear? See, the first case, in the maximum shear stress theory, the maximum shear stress is equal to sigma max is equal to 1 by 2 the square root of sigma b square plus 4 tau square. So already you know the sigma b is equal to 32 m by pi d cube. Similarly, tau also you know 16 t by pi d cube. So already we have learned that equation. T is equal to 5 by 16 into t to the power of d cube, tau into d cube. T is equal to 5 by 16 tau into d cube. So substitute these two values in this equation. So we will get the final equation 5 by 16 into tau max into d cube. That is equal to square root of m square plus t square. This square root of m square plus t square term is known as equivalent twisting moment. It is denoted by Te. So this in this equivalent twisting moment, the m square plus t square, m is a bending moment and t is torsion or torque. The twisting moment, the equivalent twisting moment may be defined as that twisting moment which when acting alone, it produces the same stress as the actual twisting moment. So that's why this twisting moment is called as equivalent twisting moment. Why should we take equivalent twisting moment here? This shaft is subjected to the combined loads. So that's why always you need to calculate the equivalent twisting moment and equivalent bending moment. So I will show you the bending moment, equivalent bending. So that the equivalent twisting moment is equal to square root of m square plus t square is equal to 5 by 16 into tau into d cube. So by using this equation, you may calculate diameter. Now, according to maximum normal stress theory, the second case, sigma b is equal to half into sigma b plus 1 by 2 into square root of sigma b square plus 4 tau square. So again substitute the sigma b value and the tau value in this equation and you will get The final equation is pi by 32 into sigma max into d cube into half into m square, m plus square root of m square plus t square. In this expression, the half into m plus square root of m square plus t square is known as equivalent bending moment. It is denoted by m e. So the equivalent bending moment may be defined as that moment which, when acting alone, produces the same tensile or compressive stress as the actual bending moment. You may written as equivalent bending moment is equal to half into m plus square root of m square plus t square is equal to pi by 32 into sigma b into dq. So from this expression, you may calculate the diameter of the shaft. This is for a solid shaft. In case of hollow shaft, so the above equations may be written as Te is equal to pi by 16 into tau into d naught cube to 1 minus k to the power of 4. So, and Me is pi by 32 into sigma b into d naught cube into 1 minus k to the 4. So, by using these two theories, you may determine diameter of the shaft. So, finally, it is suggested that diameter of the shaft may be obtained by using these two theories, and the larger of the two values is adapted. So which one is the larger value? That value you can fix as the final diameter of the shaft for our design. Clear? So like this, how to calculate the diameter of the shaft, how to design a shaft when it is subjected to both the combination of these two, the twisting and bending. Clear? So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.